Okay, so this morning we discussed quantum string systems and loop representations. The loop representations will be a little bit different, and of course the setting for quantum strings is a bit different. So I'm not entirely sure, but I assume that you know a lot about probability theory and perhaps less so about quantum strings. Am I right? Or
yeah.
Okay. But as usual, I mean, do ask questions, especially because we have until 11, but we can go a little bit over if necessary, and we can always change the extra classes. So do not hesitate to start with. Okay, so I prepared yesterday, I have my notes, but I realized that it may be better to start explaining a little bit the simpler situation of so-called spin 1/2. I'm going to describe it in details, and then I introduce the setting, which is a little bit more, a bit more general. And also I'm going to explain this loop representation first, and then we'll divide it. In my notes, I was kind of going logically until we get it, but when we don't know where we are going, it's sometimes complicated to one is in the midst of a situation and how to see what happens. So, a question: who is familiar with the Ising model, the classical Ising model? Almost everybody, but almost. So I'm going to recall it briefly. Those who did not raise their hands, do not hesitate to tell me if it's not enough. Because I'm going to start with the Ising configurations and then build the quantum situation out of that. And also, I'm going basically to write down the Ising model in a kind of a quantum way, but then we can generalize. So quantum spin systems. I can actually perhaps say that it's for values. I mean, these are very quantum spin systems, but if you for those who have ever seen something like a tensor product space, there won't be any here. Sorry, or Julia. I'm sure you know those spaces for good reasons, but I try to avoid them here. So let's start with the finite subset with D. I mean, that's as usual the domain. I mean, the set of sites. There is some geometry at some point. But here it's just a finite subset. And let's look at Ising configurations over there. I mean, and again, don't look at something too general. I mean, something which is enough is a box of the sort of size. And let's look at the Ising configurations. So you know that in the Ising model, and almost always you know, at every site you have either +1 or -1. So let's write this as sigma, and line to say that we have that's an assignment everywhere, and this is an assignment of +1 or -1 at every site. And let me write maybe capital sigma lambda to the -1 to lambda. So I mean all functions from lambda to +1 or -1. So at every site we have a +1 or -1. And okay, so then we can introduce the hyperplan. But now I'm going to introduce the quantum spins, and as you know, quantum systems involve a Hilbert space and then operators. So the relevant Hilbert space is built on balls, and let me write this as this calligraphic page with lambda. We're going to declare all those configurations using as basis elements of the Hilbert space, and then we look at all the vectors over there. So mathematically, you can write this as a little L2 sigma lambda, which means that a vector over here, if you want to write it as a column vector, you have a complex number assigned for each configuration. So I mean, there is really nothing very deep over here, but it may be just very confusing. If you are used to looking at a Hilbert space, which is like Cn, then you know what the natural element over here is. It's something like A1, An, and these are complex numbers. I'm talking about complex Hilbert spaces. So now we have something similar, except that the index is not 1 to n, but the index is based on configuration elements. Okay? So this is a finite dimensional Hilbert space. The dimension of it is, anyone can tell me, not your question, but loud. Everybody agrees with it? Gabriel did not say anything, but he voiced his opinion. So this is also the dimension and the number of basis elements. And how many using configurations do you have? Okay, it's probably more. So it's 2 to the lambda, which means that mathematically it's finite, and at the same time it's huge. So clearly something like the vector notation is not going to be very helpful. But on the other hand, we are really dealing with finite dimensional Hilbert spaces. The operators are going to be matrices, so no analytical difficulty. Okay, so this is the Hilbert space, and then we introduce so-called spin operators. And let me do it. So first, back to this notation. I'm going to use Dirac notation. So if suppose you have a configuration with this sigma lambda, then I'm going to write this cap sigma as a, as vector in H lambda, and these are the basis element. Okay. So you see, I apologize if I'm too slow, but I still remember when I was confused when I got those things. So normally we start with Cn, and then we have all the vectors of the kind A1, An, then one vector, and the set of all vectors of these forms. So this is one way to introduce this Hilbert space. You say that that's basically the set of all vectors like that, where the A's are complex numbers. Another way is to say, to do the opposite thing, which is that consider n objects, and let's call them V1 up to Vn. And then we declare those objects as elements of the Hilbert space, and then Cn, we say that this is all the linear combinations, some I plus 1 equals n, I and I actually going to write them like that. That's to remind everybody that these are the basis elements. So, and of course, each Di, if you wish, we can write it as a vector with 0, 1, and 0. where the normal one is at a high place. And then if you do it this way, then you get exactly this kind of thing. Okay? So my point is that one way to construct an invert space is that just to declare some things to be the basis, and then you look at all linear combinations. And if you want to add two such objects, obviously you're going to add one twice the AIs, so that you will exactly replicate all the operations like this. And this is what we are doing over here. We start with the easy configurations. We say that these are the bases, and we look at all linear combinations of this. So then we have this Hilbert space like that. That's the dimension. So the Hilbert space is isomorphic to C to the power 2 to lambda. So now operators, so-called spin operators. And I'm going to write them as SXI, where X is a sign as usual, and I is an index which is 1, 2, 4, 2, or 3. And so these are the spin operators, and I'm going to explain how they act on the basis. And once you have it on the basis element, then everything extends by linearity to everything. Okay, so if you have a general vector in H lambda, you can write it as a sum of the configurations and partitions of the basis elements. If you act with such operator, you just use linearity. So how do I act? Easiest is S3. S3 is the one which is diagonal in the basis element. So S3 X, when you act on this, gives you, okay, we have to put the 1/2 over here, the sigma X, and times the same thing. So sigma X is the plus or minus 1 outside X, and that's what we get. So the eigenvalues of the S3 are +1 and -1, and this is the basis over here. I mean, sorry, yeah, it's diagonal in this basis here. Then we have S1 of X sigma. This one is not diagonal. We should also keep the 1/2 over here. And it gives the configuration sigma, if you like that. And it means that this thing, so sigma X underline, is the same configurations, but the value of the spin at X has been different. So if you take this Y, this is either sigma Y, if Y is not X, and it's minus sigma X, Y equals X. Okay, the effect of this S1 is to flip the spin. So you go to this configuration to to another basis configuration. And then the S3, sorry, S2. So here since I even tell and so there is 1/2. There is actually I over 2 with sigma X and sigma will be this thing. And I have it's either this or minus, I never remember. Let me temporarily put this. And so here you also flip the spin, but in addition you have plus I or minus or plus I over 2 or minus Y I over 2 according to the value of the spin. Okay? And just to make the link with what is usually now, so multi-structure. We have the following relations. If you look at the commutator between Sx1 and Sx2, then this is I Sx3. So this has to be true. And that's what we are going to check whether the sign is correct. So we do that. I mean, if I'm too slow, sorry, you know. So I do this easy calculation. So we just check how it acts on the basis elements. So this is the commutator. So this is Sx, I mean S1, S2 minus S2, S1. So if you have Sx1, Sx2, and you add the configuration sigma, then this is like Sx1. Now we act over here. So we use exactly this thing. So we get 1 over 2 sigma x, and then we reduce sigma x. And this is a number of poles. So this can be put up front. And now we act with S1, and S1 triple spins and with 1/2. So then we get I over 4 sigma x, and then it's factored in the sigmas. Everybody agrees? Okay, then we check the other thing, Sx2, Sx1, sigma, and we get Sx2. And then when we act with Sx1, we get sigma x, or the sigma x of input. And then we apply the rule up here. So we get here, we get I over 2. We should get this.
Maybe in the first.
Oh yeah, that was 1/2. Thanks. Yeah, so I over 4. Thank you. Then now we have to integrate sigma x over here, but this is sigma x where we have 2 things. So we get the minus sigma x, and we flip the spin, so we get the sigma x. Everybody agrees? And now we look at the difference. And the difference, so Sx1, Sx2 minus Sx2, Sx1 equals this minus this. You see that we get essentially the same thing, except for the minus. So we get I over 2 and sigma x, sigma, which indeed is like, if you take the I, then you have 1/2 sigma x, that's like this thing. So we get the S squared sigma. So we have checked that on all basis elements, this operator acts like I squared. So that will probably design for. So and then I was lucky to do this. Just get to know this. And okay, so this is an important relation for spins. Then you can check that we have also all commutating relations where you take a circular commutation, so this is 1, 2, 3. So commutator S2 and S3 gives I S1, and 3 and 1 gives I S2. So you can do the same thing if you wish. Then another important relation is that if you take Sx1 squared, Sx2 squared, That's Sx3. Well, then we should get 3/4 times the identity. And right, so this is a general relation. When we are going to introduce the so-called spin S systems, which are more general than this, we are getting so-called SS plus 1 here. So that's a special case. And the reason it works here is that every single one over here is actually 1/4 times the identity. But this relation over here is to generally constant systems. This relation over here is to only equals to 1. Now it's easy to check. I mean, if you take this to the square, then you get this eigenvalue to the square. Sigma x squared is just plus 1. So you get 1/4. And this is going to work because if you are, I mean, here you get 1/4 and you flip the spins twice, so it's also working, and S2 is quite the same. So I mentioned this because if you take general spin operators satisfying both these relations and the cyclic ones, plus both, then necessarily everything looks like that. So it's just a question of choosing the basis, but then the most properties characterize characteristic properties. And here we always have this X. But we can also check that if you take the commutator between two operators at different locations, they commute. So here you can just do the operations at different sites in arbitrary order. So the combination system. So these are the spin operators introduced in the kind of probabilistic way. We have these easy configurations, and then we allow to go from one configuration to another with the hyperpole spin operators. Any question? Okay, so now we write the Hamiltonian. And the class of Hamiltonian I'm going to consider is something like H lambda is, I think I'm going to define this here, the sum over, let me write this way. So these are the nearest neighbor edges in lambda. So here I'm using the fact that lambda is a subset of ZB, and and we look at all the pairs of sites which are at distance 1. And then the operator is going to be like this Sx1, Sy1, plus here I'm putting a strange looking parameter 2 minus 1, Sx2, Sy2. I'm going to go to the elementary for logging the script so that is it like
Yeah, I think like that.
So okay, still finish. And then that's Sx3, Sy3, and what? I'm going to add an arbitrary constant to this, minus 1/4. So minus 1/4 times the identity operator. Okay. So this is going to be the Hamiltonian I will consider. The first observation. When you add a constant to the Hamiltonian, you change a little bit the function, but you do not change the Gibbs states. Because the Gibbs states, I mean, it's well, perhaps I'm going to go on this one already. It's could be easier. And also, this factor 2 over here is not essential in any way. It just helps for the loop representations I'm going to explain. But otherwise, it just rescales that correction. So, this is the kind of model we looked at, and let me immediately point out special cases. Like u equals 1, then this parameter is just 1, and then you get that the h lambda is often written as -2, the sum of the xy. The edges, and then well, it is like sx sy. Okay. So whenever you see a notation like that, it really means this thing over here. So don't look at anything more complicated than this formulation here. But really it's nice to write this in terms of kind of vectors. And this is also reminiscent to the Heisenberg model, classical Heisenberg that we saw. Instead of the spins are no longer these little vectors, but they are operators, and they execute differently. But the reason why enlarged expansion, that it's the so-called Heisenberg. The quantum version. The reason why it's very closely related to the classical Heisenberg model is that the symmetries are essentially the same. GSU2 and the other one O3. I'm always very confused about this group theory, but O3 is essentially the same as SU2. I mean, that's one. But the fact that they have similar symmetry in statistical mechanics suggests that a lot of things are similar, like critical exponents and mechanical behavior. So technically, the situation, the setting is very different, but the behavior in many respects is the same. So in particular, everything I pointed out the other day about the n equals 3 component, the same conjectures can be made over here. With the instruction and for instance, Polyakos conjecture also applies here, and so it's also that. Then the case u equals 1/2. U equals 1/2. Well, this is 0 over here, and this is the so-called XY model or quantum rotator. And the reason it's called this way, actually, it's because of a different notation, which is very widespread in the literature, which is instead of S1x, SIX. For many people, they prefer to write the operators as S. I mean, first, the sites are written with i's, and then here they write X, Y, or Z. I mean, here it could be 1, 2, or 3, and then we write X, Y, and Z. So the operator as X means what I have called S1, and so on. This is probably a more widespread, even though this one is also used. I just don't like this one because we lose this X, Y, Z, and these are very convenient variables. So I'm going to stick with this thing. But now, if you have this thing, the XY model is like that because you keep interactions in the X and Y direction. So you have like the S1, S1, and S2, S2, and not this one. But now, if you just rewrite things a little bit differently, you can just say that okay, this one and this one, and you get rid of this. It's unitarily equivalent. So in these guys, that's exactly the same model, same difficulties and behavior. So the XY model is really, I mean, that's not the standard way that this is equivalent to XY model. Now, the reason I'm writing it this way is that it's the right way to be writing the representation. Then u equals 0. Then here you have -1 over here. And then it's a strange looking model with interactions which are like ferromagnetic in the one direction, anti-ferro here, then ferromagnetic. But you can apply some unitary operations which I'm not going to detail here. And you can change the sign of two of the constants in front of these things, not three of them. I mean, if you think of easing, you can easily change the sign of interactions by flipping the spins or flipping the spins on something like this. For these things, you can actually change the signs of two of these things. So, for instance, if you have a -1 here, and +1 over here, you can change the signs of those two, and you get -1s everywhere. And then you get the Heisenberg model, but with a different sign over here, and that's the Heisenberg effect. So equivalent, unitary equivalent to the Heisenberg so-called anti-ferromagnetic. I'm not going to say more. This is true only on bipartite graphs, like this one, for instance. So the audience is disappointed because he loves non-bipartite graphs. Triangle lattice. But on the square lattice, this is true. On the triangle lattice, nothing like it. So this is a class of very interesting models, and they have been studied a lot. So now let me describe the loop representation, and then I will explain how to derive it. Any questions? So I don't suppose I should give briefly the each states. So then the particle function is going to be like the trace of the exponential minus beta h lambda. That's the trace in the inverse space h lambda. Perhaps we can just like this, so like the sum of all configurations in these configurations, and then you can write this in the application like that. Okay, and now you see the definition, because this exponential you can expand in power series. Then you will have a product of a lot of these S's, and you know how they act on the sigmas. So given sigma is going to be changed by a lot of these operations, then you take the unit product over here, and you use of course the fact that this is a basis element. So when you have the unit product between two configurations which are not equal but 0, and if they are equal, that's 1. So formally, I mean, it's not the right way to calculate it, but if you have to program a computer to do the operations are clear. So this is the constant function and the given state. So if A is an operator on H lambda, then the given state is the linear functional still normalized on the space of operations, of operators, and the expectation of A, I mean the value, the image of A, with the lambda perhaps, or right. So this is going to be 1 over z lambda, and the trace A minus beta h lambda. Okay? And now my remark about this -1/4, which does not matter at all. Whenever you put the constant over here, that just puts a constant over here. So then it affects the function functions by some exponential, the constant times the dimension of the space. And you have it over here and the 1 over z lambda. so the constant disappears. So this affects the constant function, but it does not affect the given state. And the given state is really what we are interested in. So this may place no whatever, but for the loop representation, we have to put it right in order to avoid the things from factor. And then, of course, the two over here, I didn't mention it, but beta is parameter which is the inverse temperature. So the presence of the two means that we change the beta. So that's general big state. And the correlation function. The one we are mainly interested in is, let me write this as G, xy. And what would be the expectation of the spin operator in the directions, let's say, yes, I'm thinking the lambdas. Right. So one can check that this two-point function, if you put the S1, you get the same, because there is a symmetry between the one and the free space. We could put S2, you get something different unless the U is equal to +1, in which case it's the same. So this is the kind of thing that we would like to understand. This represents, I mean, that's a generalization, well, I mean, that's a counterpart, quantum counterpart to the Green's function we were looking at yesterday. And the behavior is expected to be quite similar. So again, I mean, what I listed as what was expected is also true here, exactly the same way. So exponential decay at high temperature, exponential decay in one dimension. If you are in the XY regime, we expect the Berezinski for solid Starless transition, it's proved. If you are in two dimensions, if you look at the Heisenberg model with all the symmetry, you expect exponential decay in two dimensions, no matter what the coefficients are. That's Polyakos conjecture, absolutely not proved. And in dimension 3, you have some results about long-range order, but not for the Heisenberg paramagnet. That you have low temperatures. It's a famously open problem. Are we still recording, or but you're going to delete it, or can I make small comments about our great masters? So a partial proof about long-range order was provided, I mean, using the extension of referential stability to quantum systems, but by Dyson Big Simon. Very serious people, obviously. What they did was to do the usual thing for mathematical physicists. They first wrote a physical regulator with the results, and then they wrote a CMP paper with all details. In the PRL letter, they claimed the result also for the ferromagnetic Heisenberg order. And it was actually the Polish pointed out that there was something quite right. And they had to I'm sure they were part of that, but they didn't manage to prove it fully. So the CMP paper is absolutely correct, but the PR letter contains this claim that the proof also works for the ferromagnetic Heisenberg. It's still an open problem. Right. So they were a bit too optimistic. And so I mean, they explained the CMP paper that they had some idea of how to rewrite the Hamilton, the Hilbert space in a complicated way, which would account for this problem, but it's also so there are some results, but I'm not going to detail them too much. But what is definitely expected is that there is long-range order in 3 dimensions and higher, low temperature, and always exponential decay. So basically, we're the same things that I listed yesterday. Any question? So Now let me
Maybe,
dis-
Daniel, I can
Yes,
also
sir.
comment that there is a strict relation between this quantum spin model and bosons. Actually, the problem of proving bosonic condensation for interacting bosons, because we have talked a bit about that in the past, can be mapped to the problem of proving the existence of, let's say, long-range order in this quantum spin. So just to stress that it's all open in this context, like proving the existence of long-range order quantum system, what is called a continuous symmetry, is a challenging open problem, despite for these models based on reflection positivity that Daniel was mentioning, like at some point. So sorry, just to see that everything as a rule. Thank you.
Yeah, thanks for the comment. Perhaps I mean, if you are familiar with the bosons, we started with these easing configurations with +1 or -1 at every side. You could also imagine that this is a hardcore lattice system with either 0 particle or 1 particle. And then the counterparts to these operators are basically these Croatian annihilation operators for bosons. So there is, I mean, this setting can be mapped automatically to the hardcore bosons themselves. And then you can introduce essentially similar things. So this will correspond to the so-called off-diagonal long-range order. And then there are similar questions. And similar, I mean, part of it is proof. So the standard hardcore Bose gas corresponds to the XY model, which your question was still. So some results about the existence of Bose compensation, but also stability. And that's basically the only result which exists. So the hardcore Bose gas have not been named exactly, and nobody has been able to go beyond that. Right. So now let me describe this loop representation, and then we have a break. So loop representation for okay. So the idea is that we start with an arbitrary finite domain. We introduce an extra dimension, and we look at the Poisson point process over there. So consider well, let me write lambda times an extra direction, which is the interval 0 to beta. Beta is the inverse temperature. And now I'm start with the except if the lambda is one dimensional. So let's say that this is lambda, it's a so-called linear graph here, but it's only for the feature. And then we add this extra dimension 0 to beta. And yeah, let me with all those sides, exactly. And we consider Poisson point, I mean, independent Poisson point processes on edges. I'm going to describe in words, introduce some kind of notation, and then I ask you how much mathematical details you want me to propose. But the way it works, we go edge by edge, and for each edge, we run a Poisson point process, and we decide when we have events. And we can have two kinds of events. We have the so-called crosses and double bars. So let's say that this is the configuration over here. Here we can perhaps start with a double bar here, the cross around here, and perhaps we have the second double bar here. Then here, a double bar, cross, the cross, then cross, double bar, okay. again. So crosses, they occur with intensity U and double bar intensity 1 minus U. So here I'm assuming that U is between 0 and 1. So 1. And I hope the intensity is kind of clear. I mean, if you have so this is going to go to beta. You look at the small interval of times here, with epsilon. So you can look at this area over here and ask if one of these things, I mean, the cross or the double bar occurs, and then you have that the cross occurs with probability. And the probability is going to be the epsilon times U plus over epsilon square. So as epsilon becomes small, it's really epsilon U. And the double bar occurs with probability epsilon times 1 minus U, and again plus over epsilon square. So the epsilon square has a possibility of having more than one crosses or double bars or combinations of all of this stuff. And of course, nothing occurs with probability. And then it's going to be 1 minus epsilon, and that's probably also a little order. So when epsilon is small, it's really this thing which dominates. Okay, so you can have either a cross or double bar. Most of the time, you get nothing. And you do this. I mean, what you can do is to discretize all this interval and run the process independently of each cross. And you take the limit that goes to 0, and you look at the limiting process. So, is it clear how we generate this configuration? So if you were on a computer, imagine, I mean, you get a very good approximation by taking time intervals, and then on each of these boxes, you put either nothing or cross or double bar. Then when we have this, we look at loops. And for the loops, the idea is that we stop anywhere, and we go, let's say, up. And when we have a cross, I mean, we follow the trajectory. A cross is an instruction that we need to jump to the neighbor. And the double bar is the instruction that we have to retrace ourselves. So you see why it's depicted this way. Now we have a double bar up here. And now here we use fairly boundary conditions in the vertical direction. So here we close the loop, and that's one loop. We can start over here and see where we go. So we go up, now down. Here are the boundary conditions, and we are there. From back today, usually I have a single loop, which is not here. We can start here, and we get another loop by using the rule. Sorry, that's a cross up here. Yeah, so we finally have reached the other side, but I continue here. Here, and now we close it. And we have still one circle up here.
So what is the monitor?
Well, that's, I mean, we have very boundary conditions in the vertical direction. And then when we have double bar, we come back. So, like, in the trajectory, we're going up over here, then we go down over here. Okay. So first we have this crosses and double bars, And let's start anywhere, and we want to see the loop which goes through this point. So let's start up, that doesn't matter. So now the rule is that we go up, but here we meet a double bar. So we jump on the other side, and because it's double bar, we continue down. That's why and now we have double bar over here, we jump, and again, we change direction. I mean, exactly we follow what the geometry is suggesting. Is it clear or no? So thanks for the question. If it's not clear for some. So the trajectory, I mean, I was a bit intuitive, but the trajectory is basically you move in this at this sphere. And then you continue going up. When you meet either a cross or double bar, you need to jump. Now, if it's a double bar, you jump and you change direction. So the motion is always on these vertical lines. No, cross you continue in the same direction. And when you reach the other side, then you continue in the same direction. I mean, it's like a cylinder with very boundary conditions. So moving over here means you continue over here. And you do it until you close the trajectory. It does not matter. So yeah, so we have very boundary conditions in the vertical direction, and for the rest, we can define this on any graph. And you can think it works. I mean, if you have something like a graph which is no longer linear, but still kind of simple, you can add this you can add this extra direction, so we go from 0 to beta, and then it's okay to have this this thing, so you can have a double bar over here, a cross over here, and then you can define the trajectory to go up, here you continue over here, and it goes through. And then if the graph is more complicated than something like planar, then you cannot depict it anymore, but the definition makes more sense. Is it clear? So, I mean, why we do that is not clear, but the fact that we do that. Yes?
No, just to ask. Beta is still the inverse factor. Right?
Yeah, I mean, right here is just a parameter, but when we make a link with the constraints, yes, it will be.
And so we are saying that for every range of inverse central, we have a different jumping probability that gets big.
Yes, well, the way I do it, the intensities of these things is fixed. What changes is the extent when we do it. Now, what you could also decide is to rescale this and decide that the time interval is imaginary time is 0 to 1 always. And you put an intensity over here, which is like beta mu and beta 1 minus 2. It will give you the same picture. It's just a rescale and change of the dimensions of the approach. Yes, there are various ways of writing this, but that's my way. So why do we do that? Because those loops are going to affect the probability distribution and the relation. Can I go another 5 minutes? And then
the link, right? Yeah.
because I like to give you the theorem. So but basically the theorem is as follows. Running for 23 with only the proxies, Eisenman after the area. before with all the double bonds, right side in 13 with the combination of both. And the first thing is that if you take the Barton function, so this trace of exponential minus beta h lambda, then this is given by the expectation with this Poisson point processes, independent Poisson point processes over there. And then we have the expectations, but then we average 2 to the number of loops. Let me write this like that. So omega is the realization of the Poisson point process of the almost crosses and double bars. And omega is a set of loops. And again, the cardinality means it's the number of loops. So this is the first identity that the partial function of the quantum system is given by this kind of expectation about the loops. And I haven't put all parameters, but of course, this Poisson point process depends on beta because it's defined on this 0 to beta. So for instance, here function beta, here function beta, that's equal. So that's the first claim, and second claim is that if you take this function here, so g of xy, and the expectation of this is given by 1/4. Yeah, so this is important. And then you have a probability. Let me put the q over here of x interacting to 1. So this gives you a probabilistic description for this correlation function. That's a probability that x is connected to y. What does it mean? Well, we have the x somewhere, let's say here. And y here. We fix the time over here, so actually 0. And we look at the probability that x and y belong to the same loop. And that's it. Now, this p lambda with the 2 over here means that this is the property on loops given by this Poisson point process, tilted by the 2 to the number of loops. So perhaps I can still write this as you wish. It's also like every 1/4. And then that's the expectation. Inside loop of the 2, we have the indicator that x and y are in the same loop. But a bit smaller and still. But we get with the number of loops, and we normalize by the Boltzmann function. Yeah, that's rolling. Yeah, so I would really like you to understand this. So you see, I mean, first we define a loop model by just throwing at random all these crosses and double bars, and this measure over here, it's these Poisson point processes. These crosses and double bars are thrown around with no interactions. I mean, all the crosses and double bars are completely independent. But then we look at this kind of expression where, I mean, we basically this is away from these loop configurations or these configurations of crosses and double bars. And the weight is 2 to the number of loops. So this introduces a lot of correlations between these crosses and double bars. Okay? And then we define a probability measure out of that. And the probability measure, I mean, the probability of loop configuration is going to be the probability we get out of this Poisson point process times 2 to the number of loops divided by the normalization, which is the partial function. This expectation here. So this measure over here, this probability measure, is a probability of the crosses and double bars, where everything has been biased using the 2 to the number of loops. So this E lambda, I mean, if you do simulations for the E lambda here, it's very easy. You just call this crosses and double bars at random, no correlations. But this measure here is more complicated. We have now a lot of correlations due to this bias here. This bias depends a lot on the geometry, because the way the loops are defined now depends on the graph and so on. See here, maybe it's time, the right time for a break, and at the beginning of the next hour, I can read. I know that we want to erase on this thing.
I can keep the center part, maybe here, right?
So again, right.
Yeah.
So you can think about it, and I can describe it again. Hopefully, it will be completely clear. And once we are happy with the model, probably will be, I'll explain how we can derive it. And perhaps I'll explain this slightly more on system because there are lots of interesting other interesting models. It's what we think of it. Okay.
That's enough.
Sure. Lots of people. Yeah, thanks. All right, so we'll go with beautiful, except for this central part, which is still there. If there's still a question about this group representation, I really would like you to see this intuitively what it is. But because again, I mean, first we have the underlying graph, and in this picture, the underlying graph is a linear graph without narrow cycles. But I mean, it's just that it's hard to depict, but otherwise the model works for arbitrary finite terms. We look at this object over here, which also means that on top of each edge, we look at the time interval 0 meter, and that's where we run the point process. I mean, that's one of these small things. I mean, when you think Poisson point process, you may have an interval, which I'm putting publicly. And then you have the occurrence of events. So that's the standard way of seeing the Poisson point process. And here, the Poisson point process is on top of each edge. And inside of the dot, for the events, we have these crosses and double bars. And in fact, we have either it's a single Poisson point process with two different kind of levels. I think people call it sometimes bar process. Or in other words, you have two distinct Poisson point processes independent of one another, one for crosses and one for double bars. In any case, I mean, for each small intervals of time, you can look at what happens over there. If the time interval is small, only one event may occur. And so we have the crosses occurring with this probability epsilon times u, the width of the interval is epsilon. And double bars with epsilon 1 minus u. And so once you have the whole configurations of crosses and double bars, you have a set of loops. And the loops are defined by basically looking at the trajectories, and you follow those vertical lines, you move up and down according to the rules. And the rule is that if you start somewhere, let's say you decide to move up, I mean, I could stop moving down, continue here, but if you move up, say, when you meet either cross or double bar, you need to jump. If it's a cross, you jump and you continue in the same direction. If it's double bar, you jump and you change direction. So if you were moving up over here, you move down over here. Here, we jump, and we were moving down, so we move up. So you do these things, and then you describe this trajectory. with purely boundary conditions, relatively, and then you quickly convince yourself that you must eventually come back at the starting point. I mean, there's no way to disappear anyway. So you come back to the point, and that's the end of the loop. And then you start at any point which you have not explored, and you start a new loop and close the loop. And then here, for instance, we have here in Partnership, there is a green loop over here, a yellow, orange, and blue. So we have this example here, the number of loops is equal to 4. And it means that the weight of this configuration is 2 to the 4. And then you can, I mean, we integrate over all such configurations, and we weight like that. This gives us a measure, a positive measure. At some point, we normalize it, and we get this probability measure. But there is this parameter 2. The parameter 2 refers to the fact that it's biased with 2 to the number of loops. So if you wish, if I put the parameter 1 over here, so then we have 1 to the number of loops, so it doesn't matter. Then we see the probability measure associated with this independent Poisson point processes. And that's the loop model. And then the claim is that the trace of expansion minus beta h, so the Bottron function for the quantum system, is given by exactly this thing. The expectation with this Poisson point processes 2 to the number of loops, and the correlation functions, the quantum correlations, are given by the loop correlations in this tilted measure. So once we change the measure a little bit, we can write the quantum correlation here as the natural loop correlations. The loop correlations between sites x and y. When we fix time, I mean everything is shift invariant because we have purely boundary conditions in the vertical direction. So it's type 0. And the natural loop correlations is whether those two sides belong to the same loop or not. So this is the element which I write like x to xy. I mean, that's the set of all omegas, all realizations of these Poisson point processes, such that x and y times 0 belong to the same loop. So the probability of this element gives exactly the grid function. This is like the expectation in the given state of the S3 S3. All right. So let me just before we embark on the proof, let me point some consequences. I mean, perhaps one consequence is to attempt to interest probabilists to quantum spin systems. Yes, sir.
Do you have an easy reason to try to understand why we need to implement this process instead of just working on the loop? Like, I mean,
well, so yesterday we were looking at classical spin systems.
yeah, sure. But here, why don't we work on the why do we need to select subset of the loops with this quantum process? There.
Well, the point is that both kind of these loop models corresponds to the quantum spin systems. So if you are interested in quantum spin systems, that's one alternative way of rewriting everything.
I mean, I suspect I want to ask whether we can have an intuition from physics about this extra complication with respect to the classical case. So in the classical case, we only identify some loops.
I mean, the motivation is that both quantum spins are much closer to the actual models you want to study. The whole motivation of this is to understand the electronic properties of Commons matter systems. And this involves the spins that are carried by the electrons. So if you want to, I mean, the context of these spin systems in subatomic mechanics is to describe magnetism we like to understand why some materials are magnetic, or magnetic, or all these various magnetic properties. I mean, like some behave like magnets, and so now what is quite clear is that, I mean, if you go back to the whole background, you have electrons and ions, and electrons carry spins, and all the interactions are due to Coulomb forces. And out of this, one should understand that the matter condenses, so you form solids. Nobody has ever really understood this. And then there should be lots of interesting properties about the conductions and including these magnetic properties, for instance. And what physicists do, since everything is all too complicated, they start by assuming, I mean, since you see that we have solids, let's assume that solids are formed. Exactly why, we do not ask the question. And then we already start with a model where the ions are at fixed positions, that will be the sites of the lattices. And then you have plenty of electrons around in the continuum. It's still way too complicated. So then you can simplify things, say that the electrons are kind of associated with the ions. It's called the pipeline approximation, and simplify the interactions to get rid of lots of things. That's what Hubbard did, for instance, and you got the much simplified models where the electrons still move, but are on the sides of the lattice, and that's the so-called Hubbard model. Now you can further simplify by saying, okay, the electrons moving is way too complicated yet. So we assume that we have just a single electron at every side, and the interactions only between nearest neighbors, and it's only the spins which matter. So each electron carries a spin 1/2, which is, I mean, then the Hilbert space, it's going to be like a tensor product of this C2 Hilbert space for spins. So at every site you have the C2. And then, I mean, what first observation is that the dimension of this Hilbert space is also due to the lambda as we had before. So this one is in one-to-one correspondence with the setting I gave. So then you simplify things further, and you get like the quantum Heisenberg model. So this is the approach of the statistical, I mean, sorry, theoretical physicists, but also experimental physicists. That they want to understand already complicated things in quantum matter, and then they work with models. So they introduce models which retain some aspects, not everything. And those quantum spin systems are natural intermediates that we start with. And these are the real things that, I mean, these are very interesting things to do. Now you can further simplify by saying these quantum spins are very complicated. Let's replace all those quantum operators by vectors, and we get these spin systems that we were looking at. So this is one way to motivate classical spin systems as a simplification of quantum spins. But I mean, you see that we have a range of possible models, and it makes sense to look at different simplifications. I mean, this can be a bit frustrating, but we don't have really a good model for a given specific system. Some people may be bothered, but as mathematicians, we should like these situations. We have plenty of interesting systems, plenty of interesting questions, and we can go from one system to another. We have a whole range of possibilities. And since there is not a single system that there is any hope to fully understand, I mean, the reaction model should be just basic quantum mechanics, sometimes relativistic corrections, but probably without this you can already explain a lot of things. But plenty of particles interacting with Coulomb forces. It's quite simple, but it's totally hopeless. Because, I mean, people have not understood why really quantum matter exists, and yeah, I mean, there are plenty of open questions. So then the best way to get a good sense, I mean, if you're in the lab, you want to understand the results of your experiments, find a way to to summarize, to give you a guide of what is worth looking at. And the way to do it is to look at a lot of different simplified systems. And hopefully for different simplified systems, you get a good understanding of what happens. Then if you're in the lab, you kind of go from one model to another and extract what seems to be relevant. But for mathematicians, we can just, we have a bunch of, a huge amount of interesting systems, but quite a lot of interesting systems with different settings, and we try to extract properties. So those classical systems are very interesting. Quantum systems are also very interesting. Some things are similar, like I mentioned that most of the properties are the same in classical and quantum systems. But the way you prove it are a bit different, and then you do have differences sometimes. That's in short is part of the motivation. But for most quantum systems are definitely something that physicists are interested in. So there is a good reason why mathematicians should take them seriously. And in terms of mathematics, they just offer beautiful ways of trying to explore things. One way being to try to make them attractive to probabilists using those probabilistic representations. But of course, there are different ways of approaching quantum systems. For group representations is not the study one. But I just wanted to give you a few consequences to give some motivation for looking at it this way. But I would say that since most of you are probabilists, one way is that you can recast everything in terms of the language of probability theory, and then try to use a lot of knowledge, a lot of properties of probability theory. So I'm not sure I convinced you, but that's the best answer I can give. Well, so maybe three consequences. So first is that some correlation functions are positive. Okay, it's not such a great result, but you know that in the Ising model, the fact that 2-point functions are positive is called the Griffith's first inequality. It's not the most useful, but it's still one. It's good to have one. And when you look at the trace of these product operators and exponential minus beta h, it's not clear that it should be positive. When you write it this way, then obviously it is. So this is perhaps one of the consequences. We do get some positivity over there. Two, maybe better. I'm not going to describe this too much, but the model in this loop model, so yes, the loop model is right action positive. When you belongs to 0 to 1 half. And then out of that, you can get some results. Existence of long range order, which is basically my motivation when I was looking at this. And so then, yes. So we have existence of R and RO, long range order. So but more recently, dimerization of the 1D plane. And this was, this is paper not quite published by John Derek, Jacob, with the consumer, and why. I should put the name will be something like, hopefully this year. And that's something very interesting. So it turns out that the 1D systems in the quantum world are interesting in the ground state. Something that classical systems are not interested. It's either trivial, it's trivial. But in the quantum case, 1D systems are worth looking at in the ground state. And there is this important property of diagonalization, which can be proved using the loop representation, the fact that it's rotation positive, and of course additional lots of additional observations. And then right, it's also an interesting approach. For this. And hopefully we can employ some of the results of probability theory to gain something there. I mean, precisely about the diagonalization, there was a result by Eisenman, Dudnikova, and Barzel, and they use recent results about the random cluster model and the Fox model, and the fact that it was proved to have discontinuous space transitions exactly for Q larger than 4. And this could be translated into a result of diagonalizations for spin systems with this S larger equal to 1. I would say that this system is, which is the optimal results for the frequency check. So here you really have interesting advances in probability theory for the Fox model in 2 dimensions. And it's not obvious, but through, I mean, these 2 representations, but more, then people could make the link and get a result on the 1D quantum chain. And then also, one would like to prove the existence of long loops. And recently, there is a very interesting paper by Elboin and Sly. And they look at the model with only crosses, no 2 to the number of loops, so it's not completely related to, I mean, it's not related to quantum spins yet. But for this model, they can prove that in dimensions 5 and higher, that there is a probability, positive probability of having infinite loops. So this is something very interesting. Everything is also proved using probabilistic techniques. And this could be a first proof towards the conjecture that there should be probability language order for the quantum Heisenberg model, which is still lacking. So they don't have it yet because they don't have this 2 to the number of loops. But the kind of method that they have managed to use and develop, who knows? So perhaps they can really extend it to the number of loops. Somebody strong can motivate it to do it. So this there is a hope, but the fact that we can recast the quantum setting in terms of a loop model may be an approach to get the results. There are, of course, interesting results which are I mean, yeah, I think it is too much.
I don't have 2 to the end if you have only crosses.
Yes, you do.
But you said, maybe I didn't understand well, because I thought you said that in this paper of Slide and that works, they don't have the 2 to the end.
Which paper?
No, you just said that they
for Elboin and Slide. Yes.
Yes.
That's right. But they don't take a result for the quantum Heisenberg model.
But the partition function is written like that in their case, since they have the crosses.
Yeah, that will be the 2 to the number of loops.
So like this one.
Yes. So something I should remind you is that I mean, here we have the probability measure, and then we have this weight. And this weight is something unbounded. So it completely tilts the measure. If you look at which are the typical configurations answering these things, these are not the typical configurations for the lambda. So if we had a weight which was something like a bounded function and also bounded below, then so basically the measure with this and the original measures would be absolutely continuous. Then the typical events for one are typical events for the other. So then if you prove something for one, we can pretty much extend to the other. But here, because of this weight, what is typical for just this is no longer typical for this thing, which is still there. So the results of Warwick slide don't bring any new knowledge for the quantum spins directly. But what is fascinating is that it looked like a very difficult problem to prove the existence of long loops. And they managed to do it. And overall, they have to work hard and to get a lot of, nice methodology. And there is hope that this can be expanded forward. So just to point out, so what they do is only with the process. And so what happens is that, we go from 0 to beta. So one way to look at it, especially when you don't have this way, is that you start somewhere and then you can have the possibility of making a jump. So then it means that you have crosses up here, and then perhaps you make another jump, and then you reach over here. And since all those crosses are independent of one another, if you look at this leg, when you start at 0 and end at beta, this is a continuous time running walk. No extra complications. What becomes a bit complicated is that when you continue it, now you have to remember the information that you have left behind. You have walked up here without jumping, meaning that we know that there's no jump over here. And also if we meet over here, we have to come it back, so on. And so you can do this process. And the question is, if you are in the infinite domain, and if like this, so let's suppose this is empty, and in the high dimensions, of time is what is necessary for every slide. The question is, when you start over here, and you do this procedure, do you have a positive probability of reaching to infinity, or are you going to come back at the original site with probability 1? So everything depends on beta. Something I forgot to mention is that if beta is small, then you don't have much time for this process and double draws. So you have essentially nothing. So for beta small, the picture is that you start over here, you perhaps make 1 at most, then it's over, and you have no time to do more. So you come back and then you have a small loop. So for beta small, it's easy to prove that all the loops are tiny. But when beta is large, this can go quite some distance. So hopefully, this things is not going to affect you too much, and you can go on, and you have a positive probability of actually go escaping to infinity. So that's what I'm going to slide on. You can also talk about this because you have students on the paper. I don't know whether they have managed to make progress. One objective would be to find a way to accumulate these two number of loops, in which case it would give something about the quantum Heisenberg model. So I would say that this is one motivation for this loop picture. For probabilities, it's a way which makes it attractive to study the systems. Any question? So, the proof. Yes. So now, how do I do that? So I wanted to introduce higher spins. Maybe okay, let me just say a Jones spin S. So spin S times. So S is a parameter here, and it belongs to, it's a half integer. And we consider the configurations are going to be the following thing. So sigma lambda is equal to the set minus s plus 1 all the way to capital S lambda. So example S equals 1/2, and then the sigma lambda is minus 1/2 plus 1/2 lambda. So in fact, this is the same as reducing configurations, except that we have -1 plus 1. Now we have -1/2 plus 1/2, which is a strange way of writing it, but this is completely equivalent. But then for larger S, I mean, every time you add one integer, 1/2 integer, you add one more term over here. So the dimensional term, I mean, then we have a Riemann space, which is the L2 H lambda as before, and the dimension of the Riemann space this time is I mean it's the number of configurations, so as before is lambda, and you can check it's 2s plus 1, sorry, raised to lambda. So for s equals 1/2, we recover 2 to lambda. S equals 1, spin 1 system is also very interesting, and we get 3 to lambda, but we can go all the way. And then we can introduce spin operators in the same way. Or kind of. We can introduce S3 and in a configuration sigma. So sigma is an assignment of this thing at every side. And it's going to be sigma x sigma. So no 1/2, because before we had sigma x is plus and minus 1. But now for spin 1/2, it's necessary plus and minus 1/2. And so this works for always. Now for S1 and S2, the easiest is to introduce S plus and S minus. And again, S plus is like S, I mean, it's not lower it's really an improvement. And sigma x plus 1, square root. And then you get sigma plus delta x. So this is the configuration sigma. At the point x, you add one more. At least if you are allowed to, if sigma x is already capital S, so you're not allowed more, but then the prefactor gives you 0, and then the effect of the operator is to give you 0. Otherwise, it adds not over there. Then you have the minus here, and the minus you put the minus here, and the minus here. And when you have this, then you can define S1 and S2 by saying that S, I mean, what I remember is Sx plus minus is equal to S1, x plus minus I S2x, which you can easily invert, and then you get that S1x is 1/2 Sx plus Sx minus, and S2 x is 1/2i. I mean, it doesn't matter if you cannot really see it. The point is that you should know that it exists. So S2 is 1/2i, and S plus minus S minus. You have this?
Actually, Daniel, there is a small typo. H is minus the L2 of sigma.
Oh, I meant both sigmas.
But
That
that
makes sense.
is tiny.
I got it. Yeah, thanks. So this is one way to introduce spin operators, and then you can check that they satisfy all the relations for spin operators. But we can again define them as acting on the basis configuration basis, and we can introduce similar things. Then, so this time I'm going to erase here. When we look at the following Hamiltonian, which I'm going to write in a different way, H lambda is going to be minus the sum over edges. So that's the set of edges on lambda. And then it's going to be a linear combination of the operators B, Y, and 1 minus 2 Q, XY minus 1. And what are these operators? So I'm introducing different operators, but this is really helpful. This is a transposition operator. When you act on the configuration, what it does is to interchange the spins at x and y. So you get another configuration, but let me write it like x, y, arrow here. And I hope it's clear. That's like, I mean, at x we have sigma x, at y we have sigma y. You just need to change the two, and that's the new configuration here. So again, once you have the action of this operator on all basis elements, then you have it on the whole of the Hilbert space by linearity. And the operator Q is such that if you take, I mean, as a matrix, so you can look at matrix elements. And it's going to be the restrictions of the sigma x must be equal to sigma y, and sigma prime also must be equal to x and y. So there are strange looking operators, and but for s equals 1.5, we can check that we can write them in terms of spin operators. So we have them elsewhere. Just quickly fill in my notes. So just I'm not going to read, but it's up to how to show. So T xy is equal to 2 sx times sy. There is plus 1.5. Okay, the constant is constant times the identity. It's not very important. But the point is that if you have a Hamiltonian which is given by minus txy, then this is minus 2 times sxsy, which is the quantum eigenvalue permanent. So this operator here with spins, okay, when you multiply by 2, when you add this constant, which of course don't perfect much in this state, then this can be written in terms of this interchange operator, which exchange the two values. Okay, so exercise, prove that this is true. One way is to explicitly look at the actions of this on the basis elements and check that it's the same as this dxy. There are more efficient ways to do it, but using properties of space. And from the qxy, turns out to be equal to here. So same thing. That will have to check. It's 2 times this s1 x sy minus 1 minus x2 x2 x and y, and that's x3 x3, and also plus 1 right, like that, and plus 1 half. So essentially the same as here, except that we change the sign over here. So then if you have only the Q operator, you get minus this thing, and again, if you exchange, I mean, if you use spin symmetries and you exchange the signs of two coupling constants, we can turn this into the Heisenberg anti-ferromagnet on the bipartite block. So, and also if you take the combinations, the point is that this is exactly equivalent to the, I mean, the same Hamiltonian as we saw before, with this 2u minus 1 in front of the S1, so the S2 term. Okay, and the point is that this is defined for arbitrary S. It's also very interesting for spin 1. It can be written in a quite elegant way, and for larger spins, it cannot be written in an elegant way. But this Hamiltonian, I mean, if you start with symmetries, this is the general form of so-called ON symmetry Hamiltonians. It's not the most natural symmetry for quantum spin systems. It should be like some SUN symmetry, but it's still an interesting symmetry, and that's the general form. And the phase diagram, even in one dimension, is extremely interesting. Diagonalizations and lots of other properties. We have so-called AKLT model, the Kennedy model as a special case, and so on.
So for various values of u, you can recover the known models.
Yes. Yeah. I mean, so first, so this, I mean, it's exactly what I explained. So for spin 1/2, this is like a binary story with some of the x1, and then you get this s1 and x1. That's this 3u minus 1 x2 x2. That's x3 x3. And there was zero, no, it's quarter, it's minus one quarter. No.
For u equals 0 is minus.
Yeah, so u equals 0, that's exactly this. So you can check. But the point is that I'm going to expand this bit because this is the right way for representation. Right. So the next thing is to get to see how we can expand stuff, and I hope you will like my lemma and propositions. They are complicated to state and totally trivial to prove. So basically, the statement is the proof. So let me.
Sorry, Daniel,
Yes.
I think we want to go to the proof, or shall we postpone to next Monday? What do you think?
Oh, yeah, that's fine. I have no more than 1 hour. One hour. Should I continue? No.
Then I think.
Yes. Okay. Let me just wrap it up.
Yeah, I think it's very fine if we. I understand that then we break the symmetry of the class, because then.
Yes. So indeed, I will continue. I'll try to spend 1 hour on the proof because I need 1 hour. That's
Yeah, I
right.
think it's also
Yeah.
myself. I'm very interested to see.
Yes. Yeah. Oh, thanks for
in,
reminding me of the
detail
time.
this proof that connects.
I totally forgot them. So just in words, so I was embarking on the proof, which was fun. And then I wanted to expand this Poisson-Dirichlet conjecture. Namely, if you look at, I mean, we have loop models. We have, I mean, so we put this process in double bars. We have loops. We can also look at the length of the loops. And then the length of the loops is a vector. When we normalize correctly, it's a partition of interval 0, 1, a random partition. And the conjecture is that it's always Poisson-Dirichlet distributions in dimensions 3 and more. So what I wanted to do, and actually I will start next week, is to explain this Poisson-Dirichlet distribution, to define and to characterize it to some extent, and explain how it's related to quantum spin systems. A little bit has been proved, not much. So it's a conjecture where a lot of things can be calculated and proposed, but a lot of things involve a leap of faith for now, which hopefully people will find ways to prove gradually. That's also one motivation for these loop systems. I did not mention it, but the connection to Poisson-Dirichlet allows to understand the nature of symmetry breaking in some cases, so it's not a motivation. I will explain this next week, I guess. Yeah, so I'm done for today, I guess.
Excellent.